Hello everyone. In this video, we will be discussing about some of the examples of axisymmetric element. Already in video 1, we discussed the introduction about the axisymmetric element and its axis. So this video will be useful for us to understand more about some of the practical examples of the axisymmetric element. So to begin the session, we shall again recollect the definition with respect to the axis. So in a triangular tori, so this is a triangular tori where the axis has been defined as z, r and theta, or even sometimes even we can call it as z, r and phi also we can use it instead of theta. So each element is symmetric with respect to the geometry and loading about z axis. So this particular z axis here you can able to see here, this is the z axis. This particular z axis is called the axis of symmetry or the axis of revolution. So some people they call it as a symmetrical axis. Why it is called as symmetric means because with respect to this particular axis only we will be rotating the 2D element. So that is why people call it a symmetric axis. But the correct meaning is nothing but the revolutional axis, because we will be revolving the 2D element with respect to this one. And what is the nodal points here I will be using for denoting the 2D element which I have taken is LJM I have taken. But there is no proper rule that we need to go with only LJM. You can go with IJK or whatever the alphabets which you are comfortable with. That only for the node location purpose will be going with that. And again this is not a proper example. Even you can go with any other example where instead of the 2D 3-noded triangular element you can go with the 4-noded or quadrilateral, anything, any 2D element here we can able to consider. So these three axes how to remember and what we call. So r, phi and z, as I told you, instead of phi even we can go with theta also, but there is no change in the r and z. And some people instead of the z they go with y, but usually we will land up with the confusion because in the same subject we'll be discussing about 2D elements also and 1D elements also. So to avoid the confusions, my suggestion is go with Z as the rotational axis or the symmetrical axis. So R is nothing but the radial axis, and phi or theta is nothing but the circumferential axis, and Z is nothing but the longitudinal direction. Examples, this is very important. Directly if you want to solve the problems means hardly two or three problems you can able to solve it, but if you try to explore with more examples of the axisymmetric elements, then it will be very easy to understand, understand the concepts, and even any problems with any complicated shapes also you can able to solve it. Here I have taken two examples. The first one is nothing but domed pressure vessel, and second is nothing but the engine valve stem. We'll discuss one by one. First one, for the domed pressure vessel, the ring torus, the torus part I'll be talking about, where the full view and the cut away portion, both the views is shown here. Even the cross section of this thing also shown here. See, understanding is very important. I think everyone would have studied in their first year engineering about the designing, the front view, top view, side view and other things. So here you can able to see here for the domed pressure vessel, what is the x-axis, y-axis, z-axis. Correctly speaking, what is r? That is nothing but the y-axis. Here I'll be calling it as r, and the angle of rotation phi or theta, and even the radius r. That also here I will be you can able to see here. So with respect to this dimensions only, this full view and the cut away view is shown. And for the ring torus part, and next one is the horn torus part. Horn torus part, again you can able to see here where the center, the diameter has been reduced for this one, and even the cross section also you can able to see here. So this distance actually decides the total the radius. So you can able to see the total radius, even the gap in between. So here you can able to see a huge gap, but here actually speaking there is no gap. And next one is nothing but the spindle torus part, where it is both the circles is present or lapped over on each other. So ultimately what is the kind of sketch we'll be getting means, here you can able to see in the cutaway part. This is the full view on the cutaway part you can able to see here for the spindle torus. So have you look on this one. Even if any other like cylindrical part or these kind of applications or the sketches, then means do analyze. Then only you will understand the in full view how it will be seen, and even the cutaway view and even the cross section view how it will be seen. So next is the derivation of the stiffness matrix. Before moving to the derivations, of course, we should have some clear-cut instructions. So axisymmetric element, so R, Z, and phi, where this can be still clearly discussed as x and y axis. So here the deflections I'll be denoting it as u and y. For the three node or 2D element, I, J, K is the node numbers. I'll be going with that. In case if any other 2D element, but which has some complexities in the shape, means you can go with more number of nodes depending upon the requirements. Example, if I'm looking for a 6 nodes, means I can go with I, J, K, R, L, M, N. And if it is a proper 4 noded 2D element, means I can go with I, J, K, L. And again, a proper or a improper rectangular shape, means depending upon the shape whatever we have, we can go with IJKL and MNOP. So these are all the examples and even the nodal notation I have used. It is not compulsory you should go with the same thing, because actually the given continuum decides what should be the number of nodes and the node locations, everything. And moving to this particular thing, which is nothing but the plane cross section and even for the axisymmetric element. So you can able to see here this particular portion only, that is the cone frustum, the frustum of cone part, where only a small panel I have taken, and how the 2D view with the node numbers has been defined. You can able to see here, and both x and y axis. So theta here I have, that is the thing with the circumferential angle, and r and z, the vertical axis, that is longitudinal vertical axis. Here you can able to see here the 2D element you can able to see here. So have we look on this particular sketch theta, where d theta is something but a smaller angle that should be defined here. Otherwise we can't able to do the derivation, because always any derivation it is possible to do for the small panel. Later we'll be integrating for the entire model. If theta is the angle of rotation, d theta is a small angle where the projection has considered, and a and b is the this particular portion which I have taken for the derivation purpose, and C and D is nothing but this particular thing. So we know like A to C and even B to D distance. So this particular projection line I'll be going with U, and for the AB line it is U, and for the CD, which is nothing but U plus dou U by dou R with respect to the into dou R. So this a small thing already we have discussed many times. So a small angle, again the projections of that one, and how the deflection should be defined. All those things we have discussed multiple times when we derived the derivations in the previous chapters. And assume that this is an example where actually we will be discussing the derivations. A cylindrical, of course, an internal pressure will be there, and how the internal pressure should be shown. You can able to understand that usually a boiler kind of examples, if you are going with that, means the pressure will be there on all the sides, and how this pressure should be defined, that we should be knowing. Here have you look on this one. First of all, if I'm going with R, or if you're going with if you're calling it as the X max, we are calling that as the radial stress. And second is nothing but the row, like the internal diameter thing, that I'll be calling it as the hoop stress. And next one is nothing but the axial stress. So all these things how I'll be denoting means sigma R for the radial stress, and sigma theta or sigma usually sigma R or sigma phi I'll be going with the hoop stress, and sigma Z for the axial stress. Whatever the axis we are denoting here, the same thing we need to show in the suffix of the stress what we are using. So have you look on this particular sketch, a cut view of an preferably a boiler example, the pressure vessel, and this arrow mark indicates the pressure which is acting inside the boiler